So welcome to the lecture on design via root locus and compensation techniques. Today we will discuss about lead and lag lead compensation. So we discussed about in earlier lectures the lag compensation technique, and we know that the lag compensation technique was a passive compensator equivalent to the ideal integral compensator, that is PI compensator. So similarly here the lead compensation is passive compensator for the active ideal derivative compensator. So here the PD compensator that we discussed in active circuit, we can use here the lead compensation technique. So when we remember the active derivative compensator, that is ideal compensator, PD, and we also call it PD compensator. So we put a 0 close to the origin to compensate that system, because the PD compensator we use to obtain the transient response, the desired transient response. And so we put some 0 and we put some 0 so that the angle that is made by the desired location of the pole is odd multiple of 180 degree. In case of passive network, it is not possible to put a single 0, rather a 0 and a pole will be resulting in passive network. So here in case of lead compensation equivalent to the active ideal derivative compensator, we will put a pole and a 0 so that the angular contribution of the compensator is still positive, and thus we will approximate an equivalent single 0. Because if we put the pole very far from the 0, then the contribution of that pole in terms of the angle will be very less in compared to the 0, and that can be an approximate compensator for the transient response. So here we can see that we have here the 0 of the system, P1 is the pole, P2 is the pole of the system. Now this is our desired pole location where we want the new root locus to reach to this point. So we are putting a 0 here and we are putting another pole, that is compensator pole, and we can see that the angle, that is theta 2 minus, so theta 2 is due to 0, so it is positive, minus theta 1, so this is negative, and minus theta 3, that is negative, minus theta 4, plus theta 5 equal to 2k plus 1, 180 degree. Now here theta 1 minus theta 2 is theta c is the angular contribution of the compensator. Because we are putting a 0 and a pole, so the angular contribution of the compensator is the difference between these two angles. We can see here theta c, here theta 1, theta 2, and theta c is theta 1 minus theta 2. So theta 1 minus theta 2, we can see that we can find this theta c such that there are several options to set this theta c so that we can reach to the desired pole location. So we can put like here the pole, the 0 and pole. So we will have this angle, and we are going to have some desired pole location, and this option also will give us the same desired pole location, and similarly this option, that is the third option. So there could be infinitely many choices for putting 0 and pole of the compensator, so that it will provide the same theta c. However, we will be able to get the desired tangent response because we will be able to put the desired pole location, but we will the different choices will differ in terms of static error constants, required gain to reach the design point, and justification of the second order approximation. So although we will get the desired tangent response, but we will get different static error constants and so the steady state error. So here if we want to design the lead compensation of the system, first we have to find the desired pole location and then we have to select some values of 0. So we assume some 0 location, and for this desired pole location and from this 0 we must compute the angles that is being made by on this point by this 0 and the system poles. So we can see this example here in this figure. We see that first we put a 0 to get this desired pole location, and so we calculate all the angles, that theta 2 minus theta 1. So not theta 1 we have to calculate. If we assume that by putting this 0 we are able to get some angle here, and that is not 180 degree, but there is some difference, and that difference will be fulfilled by putting a 0 at that location, so that the theta 1 we will get to satisfy this condition. So here first we will put the 0 and we will put the pole at that location where it will satisfy the angle condition for this desired pole location. So we will see some example when we will discuss the example for the lead lag compensation. So now we come to the lag lead compensation. So we have already studied the lag compensation and we discussed the lead compensation. Now we know that the lag compensation is an equivalent for the transient response. This lag compensation we use for the steady state error desired to get the desired steady state error, and this lead compensation we use to get the desired pole location or desired transient response. Now we saw that when we design for the desired pole location or desired transient response using lead compensation, the steady error constants may vary, and therefore we should combine these two, the lag and lead, so that we can design for both, that is steady state error as well as the transient response. So here lag and lead compensation, we will use both the techniques. So the steps are that first we have to determine the desired pole location based on the specifications. So what is our design requirement? Based on that we have to determine the desired pole location. So the pole location is mainly decided by the transient response requirement, like percentage overshoot, settling time, peak time, and so we will find the desired pole location, and for that pole location to obtain we design the lead compensator to meet that transient response specifications. And when we use the lead compensator, we will get that we add a 0 and a pole for the compensator and some gain we will add to this in this design. So one additional compensator pole and 0 will be added to the system. Then we simulate the system to see whether we are meeting the transient response requirements or not. If not, we will redesign. If yes, we will go to design for the lag compensator. But before designing for the lag compensator, we have to evaluate the steady state error performance of the lead compensated system, because our uncompensated system has certain steady state error performance, but now we have designed that system is augmented by designing the lead compensator. So the steady state error performance will be changed with respect to the uncompensated system. So when we come to design for the lag compensator, we have to see whether the lead compensator has changed the steady state error performance, it has improved or not, and with respect to that we will design the lag compensator. So once we have designed the lag compensator to yield the required steady state error, then we will simulate the system to see whether all the requirements have been met. If not, we will again go for the redesign. So here we will take one example for this. So let's take one example, and in this example we will use both the lead and lag compensation to design for the transient response as well as the steady state error. So here we have a question that we have this system, and this system has, this is our GS, KGS, and this is CS. So we have to design a lead lag compensator so that for 20% overshoot we get the dominant poles at 20% overshoot, and the settling time is half of the uncompensated system. So if I say TS0 is the settling time of uncompensated system, this is uncompensated system. So this is uncompensated system. So we design so that we get reduction in the settling time, so that is half, and we want that the steady state error is 1/10 of the steady state error of the uncompensated system. So here we can read this problem that for the given system design a lag lead compensator so that the system can operate with 20% overshoot and a two-fold reduction in settling time. Further, the compensated system can exhibit a 10-fold improvement in steady state error for a ramp input. So here this is a type 1 system, so the test input will be ramp. So this is type 1 system. So now when we want to design the system, first for these conditions, first we have to calculate this settling time and steady state error for the original system. So here, so we will calculate the 20% overshoot. So this is equivalent to damping, that is equal to 0.456. So this we can calculate because there is the formula between damping and overshoot. So we can calculate the damping, and this will value of damping we have to, so the root locus must cut this line of damping line, then only we will get a point that will satisfy both the condition, that will be on the root locus as well as on this damping line. So here let's plot this. So we have open loop poles at s equal to 0 at origin, at -6, and here at -10. And this is a line for damping equal to 0.465. Damping equal to 0.456. Now this root locus will start. So let's use, it will start, this angle is so this is the angle, and this angle is 180 minus this angle. So root locus will start at poles, and at this will break away here, and this one will start and go to infinite. Here there is 0, infinite, no any finite 0. So all these three poles will lead to infinite as a root locus. So here they will bifurcate at some point between these two, and this will go and cut this line at some point. So this point we can find, we know how to find these points, and this point where it cut is minus 1.794 plus j 3.501. So if we so minus, so we will get this other point here, and this happens for k equal to 192.1. So this is the gain, and we will get the third. So these are the two poles, and here we will get somewhere the third one pole. So this is the uncompensated system giving the 20% overshoot for these dominant poles at A. Now we can calculate, we will go for the, so this angle is 62.87 degree. Now we will go for step 2. That is the lead compensator design. So we will design the lead compensator here. So here we have to, we know that the settling time should be half, and we know that settling time Ts equal to 4 upon sigma d, that is zeta omega n. Sigma d is the real part of the pole. So here if we want Ts half, this sigma d should be double. So here sigma d equal to, so here is the real part 1.794 into 2. So minus 3.588. So we will get this sigma d. Now we know sigma d. We know here sigma d, and this is omega d. So here is sigma d, omega d, this is omega d, and this is theta. So here tan theta equal to omega d by sigma d. So this is tan theta, that is this damping equal to 0.456 line, that is 62.87. So here omega d equal to sigma d into tan 62.87, and sigma d we put this value 3.588, and we will get 7.003. So we got omega d. So to obtain this transient response condition with 20% overshoot and half the settling time, we must obtain the pole location at minus 3.588 plus minus j 7.003. So this is our required design condition. So the dominant pole must be here. So this is design point. So let's now, when we for the lead compensator design, we have to design a 0 and a pole. So a 0 we select, let's select arbitrary. So we select ZC equal to minus 6. So we select a 0 at minus 6, and then we calculate, we try to find the PC. So we have to find the compensator pole. To find the compensator pole, so let's say we have selected here. So now we plot this point B. So let's say this is minus 1.794, and now we are double of this. So this is the damping line, and our point is here somewhere, this point, that is point B, minus 3.588 plus J 7.003. So this point we have to, we located a 0 here. Now we have to, that is ZC, there is already a system pole here. We put the compensator 0 here. Now we have to calculate these angles. So here this angle, and there is one system pole here. So this angle. So these angles, so we do know that these angles will cancel because there is a pole and 0 here, and this angle and plus this angle we can calculate. So this angle is coming equal to minus 164.65 degree. So this angle, so sum of angles to the design point from the uncompensated system poles and 0 and the compensator 0 is coming minus 164.65 degree. Now if we want this point to pass through the root locus, this point must make angle of minus 180 degree. So we must put a pole somewhere. So let's we put here some pole PC, so that the angle contribution, this angle contribution, this, let's say theta PC. So this angle contribution will make this angle to minus 180 degree. So here the difference is 180 minus 164.65, and that is 15.35 degree. So we know that when we add a pole, it will add some negative angle. So we must add this minus 15.35 degree, so that in this angle, and it will make minus 180 degree. So from here we can find the PC. So PC is, we have this sigma j omega axis. Here we have put this ZC, and this is our pole location, and this is our PC. So here this is minus 3.588 and this is J 7.003, and we want that this angle theta PC, so tan theta PC equal to 7.003 by so PC minus 3.588. So this upon this, so this is PC and this is here 3.588. So we are going to get this PC minus 3.588, and that is this theta PC is tan 15.35. So this is 15.35 degree. So from here we will get PC. and that is minus 29.1. So we are getting this PC at minus 29.1, this third pole, compensator pole, sorry. So when we have obtained this, we have a lead compensated system, and the lead compensated system is this. So we have now this B, that is minus 3.588 plus minus J 7.003. We have here system pole, compensator 0, system pole, and here is the compensator pole. And so this is the, and now this root locus must pass from, so we can plot here. So here now our system is one pole at this point, then we have here one system pole here and system pole here, and we have compensator 0 here and compensator pole here at minus 29.1, and this is the damping line. So now the root locus will start from this pole, it will start from this pole, and it will break away. The pole that may start here can lead to this point, this 0, and this may lead to infinity, because we have these three poles leading to infinite, because there are only one finite 0 here. So this locus here cutting at this point B and we get this minus 3.588 plus minus J 7.003 for our gain K equal to 1977. So we are getting this at the value of gain K equal to 1977. Now the step 5 is to design the lag compensator. So we have designed the lead compensator, and the lead compensator has transfer function GL, lead compensator is 1977, because K is 1977, S plus 10 and S plus 29.1. So here we see that when we put the compensator 0 at this pole location, they will cancel out. So this 0 at S plus 6 cancelled this pole, system pole at S plus 6. So this is the lead compensated system's transfer function. Now we have to go for lag compensator. So lag compensator we have to design. So we know that the uncompensated system has, so GS was, and we had the gain K equal to 192.1 by S plus 6, S plus 10. And from here we can find KV0. So we say KV is the velocity static error constant and 0 is for the uncompensated system. This is uncompensated system. And when we calculate S equal to tends to 0, we will get this 192.1 by here 60. So that is 3.2. Now for the lead compensated system, we will get KV lead, and this we will get, we have 1977 by 10 into 29.1 and we will get 6.794. So the objective was to design for the steady state error. The objective was to design the steady state error 1/10 of the uncompensated system. So now we see that KV lead compensated by KV0 equal to 6.794 by 3.201. So we get it 2.122. So we have already, and this is the ratio, this ratio is the ratio of the steady state error also. So we have already improved the system in terms of steady state error 2.122 times. So steady state of the error of the lead compensated system is 1 by 2.122 into steady state error of the uncompensated system. So our target was to design compensator for 1/10 of this. So now for the lag compensation we need only the improvement, that is 10 by 2.122. Only this much improvement we need by lag compensation, because we have already achieved this much improvement by lead compensation in terms of steady state error. So that is 4.713. So 4.713 we need, and we know that, so this is equal to so KV so this is the 4.713 and that is KV lag by KV lead. So in the lag compensated we will get improvement in terms of lead by 4.713 times. So now when we design the lag compensated system, we will select the location of the pole near the origin. We know that to design the lag compensated system, first we select the pole at some position close to origin. So we select that pole at 0.01, that is close to the origin, and we know that ZC by PC equal to KV, this value lag by KV lead, so equal to 4.713. So ZC equal to minus 0.01 into 4.713, that is equal to minus 0.04713. So we got this location of the lag 0 of the lag compensator. So we have, so the compensator, we have S plus 0.04713 by S plus 0.01. So this is the lag compensator only. And so the transfer function of lead lag compensated system is equal to, so this compensator, we have this lead and this is lag. So now the total compensation is K S plus 0.04713 by S plus 6, S plus 10, no, S plus 10 here, and S plus 29.1, and here S plus 0.01. So this is the transfer function of the lag lead compensated system. Now what is the, now we can plot this root locus, and so here we can see the system here, the root locus of the lag lead compensated system we can see here. So one pole at origin, then this pole at minus 0.01, there is a 0, and this, and the root locus is passing through this point, and this is the response of lag lead compensated system, and this is uncompensated, and we can see that we have improved the transient response as well as the steady state error. And here we can see better the steady state error for a ramp input. We have this lead compensated, and when we apply the lag compensation, we have further improvement in the steady state error. So this example was taken from NICE NS Control Systems Engineering. So I thank you for this lecture, and let's see in the next lecture. Thanks.